and I have the great pleasure to have to chair John Gower. I think that everybody knows the works of John. We have been was published a lot of papers and books about biplots, procrustes analysis, distance-based methods. John is now at the Open University after having spent a long while at Rothamsted Experimental Station. So, please, John.
Well, I will join everybody else in thanking the organisers for asking me here, and special thanks to Jerome for providing me with a bar stool on which I feel more comfortable. I'm told I have the name of my department wrong. It's the Mathematics and Statistics Department. I thought I'd better start off with some general comment as to what a biplot is. I'm sure everybody knows, but what this says is that biplots simultaneously display two kinds of information, typically the variables, and these can be either categorical or numerical, and sample units, described by a multivariate data matrix, or the terms labeling the rows and columns of a two-way table. I distinguish very much a data matrix and a two-way table. They're both two-way arrays, but they're different kinds of things. And approximation is very important. The last part of the slide I think is best ignored because you all know the kind of area we're talking about. Now, Michael Greenacre asked me to make some kind of historical remarks, when I should try and make a few, but I should give up after the first 10 minutes or so. Where do I think biplots originate? Well, I think it's Ptolemy. This is Ptolemy as depicted by some later artist, because Ptolemy lived in the 1st century AD and was based fundamentally in Alexandria. And I looked up Wikipedia to find out more about Ptolemy, and you won't be able to read that, so I shall read the important bits again. He wrote a book called the Geographia, and the first part of that discussed the data and the methods he used. Ptolemy put all this information into a grand scheme. Now, following Marinos, and maybe we should be paying respects to Marinos, because following Marinos, he assigned coordinates to all the places and geographic features he knew. And in a grid that spanned the globe, notice the word globe, it's fascinating, back in the 1st century AD, latitude was measured from the equator, as it is today, but Ptolemy preferred, in Book 8, to express it as the length of the longest day. They didn't have ways of measuring degrees, but they knew the day length, and this is near enough. So, not going to all these other details, that's exactly how he did it. He had a grid, and I will now show you a very, very early biplot. And this is Ptolemy's map of the world, a very early version of it. And, yes, somewhere round about there is Rennes. It's really not a bad map of the Mediterranean world. Most of the features are recognizable now. It has, the origin is somewhere around here by these dots, the Cape Verde Islands, it is believed. And there is a grid stretching longitudinally, and latitudinally you can see it. There it is. And there are various places marked on it. So it is a biplot. It has axes representing variables, coordinates, and it has places marked on it. And clearly, it is an approximation. Doesn't seem to want to move on. Right. This is a later version, still pre-Columbian, so this is before America had been discovered. You can see the grids on here much more clearly, but it's noticeably much the same map as the much earlier one. I don't think I need really say more about it, but just to stress the fact that there was a coordinate system well known nearly 2,000 years ago. And this says all the things I've already said, and stresses at the bottom, and doesn't really concern us, that Ptolemy seems to have recognized that the world is a globe. Now I move on 1,500 years, and we have here someone you all recognize as Descartes. Now my French is very bad, but I believe Descartes translates to of the maps. Am I correct? Of the maps, Descartes? Yes? So following Ptolemy, we still have maps, and some people, and Michael is one of them, and I like this terminology, often refer to the kinds of diagrams we're discussing at nearly all these talks as maps of the data. So maps is a good word, and Descartes has a good name. I believe also he is a local boy. I think he comes from Normandy, not so very far from here. Now I've got this from Wikipedia. I've given up Wikipedia after this slide. But it says here that this system, this is the Cartesian coordinate system, was developed in 1637 in 2 writings by Descartes, and what I didn't know, independently by Fermat, unpublished, in Toulouse presumably. And he introduced the new idea of specifying the position of a point or object on a surface using 2 intersecting axes as measuring guides. In La Géométrie, he further explores the above-mentioned concepts. The last bit of this quote merely says that artists in the Renaissance used grids to help in their paintings and in various other ways. But I've already pointed out that the idea of a coordinate system had been around for a couple of thousand, or 1,500 years. I don't think we can say that Descartes invented a coordinate system, but of course what he did invent was absolutely fundamental to what we are now talking about, is the way of linking a coordinate system to geometry and making geometry algebraic. And without that, we wouldn't be getting very far nowadays in any of our analyses. Before you can write a computer program, a computer algorithm, you really have to have it in algebraic form. And without the work of Descartes, that fundamental step would not have been possible. I mentioned that biplots, an important aspect of biplots is that they're concerned with approximation. 2 main types, this isn't a complete list by any means, is one you're all familiar with and has been mentioned several times already through the least squares properties of the singular value decomposition. And this will come up again and again. But also by using any form of multidimensional scaling, it doesn't matter what, to represent the cases, and then superimposing information on the variables on top of that. And there are 2 methods that I know for doing it. One rather well-known regression method, which regresses the values of the variables on the positions of the coordinates of the points. And something which I developed long ago, or some while ago, called nonlinear biplots, where all you have to know is the distance of any point from any of the from all the cases, and that will allow you to put that point on the map. And if that point represents a value of a variable, you can trace the locus of that, and that becomes a locus of the variable in the multidimensional scaling map. So these are 2 main classes of approximation. So the singular value decomposition, so this is still history. Thing I've often said, and other people stress it, but it still gets a bit confused. The singular value decomposition is unfortunately not a nice centenary, but 1873, 1874 was the great year for the singular value decomposition. It was when it was discovered by algebraists. And I remember Robin Simpson, who some of you will know, rather disparagingly dismissing the singular value decomposition as an obscure result in algebra. And it might have remained an obscure result in algebra if it wasn't for the work of Eckart and Young in 1936, which established its least squares properties. That's why it is so important to us. And if you want the best rank R fit to a matrix X, then you can get it through the singular value decomposition. So people tend to sort of refer to Eckart and Young, which is quite right, but it is this least squares property, not the singular value decomposition itself, that we ought to be thanking Eckart and Young for. And then I more or less end my historic phase at the beginning of the biplot era with Ruben Gabriel, whose famous paper in 1971 introduced the word biplot, and he was interested in biplots for both two-way tables and for data matrices, and he developed diagnostic biplots, that's with Bradu and Gabriel, and canonical biplots, and he did a huge amount of work in this area, as everybody knows, and we thank him for that. At the bottom of the slide I put Paul Horst ? This is because I remember 20 years or so ago it must be, talking to Willem Heiser, and I seem to remember him saying that Paul Horst had been using biplots in the 1960s. So I emailed him, not Paul Horst, but Willem Heiser, and this won't be readable probably, so I shall read it to you. He took a long time to reply because he's a busy man, but I got a reply only last week. And this is what he says. He says, what I recall is that I said Paul Horst had written about direct decomposition of data matrices rather than defining factor analysis in the usual way as decomposition of secondary structures such as the correlation matrix. Now, I'm very much in favor of always going back to the data matrix, or not correlation matrices, or even distance matrices, but getting right back to the data so far as one can. And Willem remarks then that Paul Horst was a man of numbers, not plots, so I don't believe he actually plotted the coordinates obtained. At least I couldn't find that back. And then he says, see his book Factor Analysis of Data Matrices, and note the data matrices in the title. In chapter 3 he introduces the singular value decomposition, and in chapter 4 the decomposition of the data matrix is the basic one from which other methods follow. Then, a rather sub-issue so far as I'm concerned, chapter 22 gives an interesting treatment on homogeneity analysis, which is very, very closely related to multiple correspondence analysis. Some would say it is the same, some would say that there are philosophical differences. 10 years before Giffey started to make a whole system of it. And to Willem's surprise, it also contains a method to eliminate the horseshoe effect in multiple correspondence analysis. So Horst certainly had an important contribution to make in the 1960s to the use of singular value decomposition for describing many methods of multivariate analysis. And that is an issue that I would like to take up in a moment. And first of all, I'm going to stress that biplots are not a method of analysis. I'm not going to be talking about methods of analysis, hardly anyway. They're only ways of presenting graphically the results of a variety of multidimensional methods of analysis. So I've just said I'm not going to talk about methods of analysis, but I note that the main differences between methods is often one of the initial transformation of the data X, which is the sort of thing that Paul Horst was doing. Now here is a slide which you don't have to take in detail, but these give you some common initial transformations. In principal components analysis, of course, you center the data and you usually often normalize it. You may just log it, which is an alternative if the data are all positive. You can remove main effects from a two-way table. That's removing row and column means. And you can do that on the log data or on the original data or any transformation of the data. Correspondence analysis, I know I find that this is a sensitive matter, but I'm not going to make a big issue of it today. But there are, I think, several varieties of correspondence analysis. Two of the most important are the direct representation of the contingency table normalized by the square roots of the row and column means, or the one which generates chi-squared distances. And that's, we will see, instead of r to the minus half, there's an r to the minus 1 for row chi-squared distances, and there's a c to the minus 1 rather than a c to the minus half. So there's a small change there. You might work out within group dispersion in canonical variance analysis and transform to canonical variance, and then you just are back in the principal component situation. You might, rather than analyze X itself, actually want to analyze a correlation matrix or a covariance matrix, or a dissimilarity matrix of some kind. A multidimensional scaling is in there. Or the bottom line, that's multiple regression, y minus xp. You might want to constrain the regression coefficients in some way. And this just notes that if B0 is the ordinary least squares solution, the left-hand side, y minus xp, splits into two orthogonal bits, whatever the constraint. And so all you have to do is to minimize over B, the constrained B, the fit to the ordinary least squares solution. And reduced rank regression comes in there, and Canoca, I believe, comes in there as well. But as methods of analysis, I'm not going to be discussing these. Other people already have or will be talking about them in this meeting. Now, coordinate axes or coordinate systems come in a variety of forms. The top one was Descartes, if not Ptolemy. And there it is, a nice even labeling of the axis with numbers. The second one is more irregular, but it is still systematic. It might represent something like a log transformation. C, the third one, I can even use this mouse. There it is. The third one is totally irregular, and that can well happen if you have used some form of optimal scaling without any further constraints, so to produce optimal scale numbers, and they may have that kind of situation. Nonlinear axes, of course, in D, certainly nonlinear. These will arise from using peculiar kinds of distance, and although in principle you could have regular scale marks along there, in practice it will never happen. Here we have categorical variables. Categorical variables, and we'll come to it in a minute, are defined by what I call category level points, which we'll come to in a minute. But here we have ordered categories, which define regions in space which are not the same size, but they're nice regular regions. You could draw a line across it, as I've done down the bottom, and there is small, medium, and big, and here are small, medium, and big, and these points here are just the centers of the dark grey, light grey, and white bits. Now, to ask what the value of a case is, you will project onto these axes. In these situations, you ask which region is it in. In this form here, which of these small, medium, and large coordinates, in inverted commas, points, is it nearest? So it's nearest rather than projection. And projection, orthogonal projection, is a special case of being nearest something. But it's more general. This is just the concept of how near, what is the smallest distance of a case to some kind of marker. And the last slide is a categorical variable with 1, 2, 3, 4, 5 category levels, and these define convex regions. There are category level points, and these are nearest neighbor regions in the full space to those category level points. In approximations, they're not so simply defined. They do define convex regions, and again, you're interested in which region your sample points lie. Tools of interpretation. Well, the inner product, of course, is one of the most used. Distance, frequently used. Area, sometimes used, and I shall mention it. Angle is important. Even if it's only a matter of projections, right angles better be right angles, so you better get your angles right. But of course, if you have inner products, you might want to have the cosine of an angle, so you better get that right as well. Orthogonal projection I mentioned. Nearness I have mentioned. Convex regions I have mentioned. Content. And I was asking Gilbert this morning what the French for content was. And apparently there isn't a word. 2 points you have distances. For 3 points you have area. For 4 points you have volume. And in English, if you have 4-dimensional objects and 5-dimensional objects, they have content. It's the generalization of volume. And I think Gilbert told me that the French is always volume. It doesn't matter how many dimensions. So these are interpretive tools. How do we present inner products? Right, even if inner products are one of our interpretive methods, there are many ways you can present an inner product. 2 sets of points, or vectors if you prefer, and you work out AB cos theta. You all know about this. And of course you can do it by projecting A onto the B direction, that's A cos theta times B, and you work it all out. You can have 1 set of points as a calibrated axis, which is what I like. But I admit it doesn't always work if you have a lot of axes. You can do it in terms of areas because AB cos theta is also AB sine of theta plus a half pi, and that is an area. In some ways it doesn't matter what method you use, but in any published diagrams it should be absolutely clear to the reader what method of interpretation they are going to have to use to understand the map they are looking at. And doing some work with a few people in Erasmus University, trying to build up a set of little, we call them cartouche, little signs to say what methods of interpretation are valid on a particular map. So I thought I'd better show you a biplot. This is a fairly simple one. I wasn't going to mention the fact that we have written a new book, Gower, Lubber and Leroux, called Understanding Biplots, and this is our front cover. It is published about a month ago, and you can buy it from Amazon. I've never seen it. That's the front cover. It's a principal component biplot, and you can see, or perhaps you can't, you can see that there are calibrated axes going through an origin. You can also see there is a red point in the middle called target, and this is about quality control, process quality control in a factory. So they want their variables to be such that their products are there, or at least within the green region. The red region is bad. The blue region means you better do something about it, try and get the process under control again. The yellow line is a smooth version of monthly positions in the factory. And you can see, I think it goes this way, that it stays under control all the way through here, and suddenly goes blue and then red, but they turn it round and it comes back, and it looks as if it's heading towards a bad region again. So anyway, it's an ordinary principal component biplot, but it does show that there are some novel uses even for that, and it does show some calibrated axes. The black points are the different months. Now there are lots of things you can do to preserve inner product. Rotations, we know, make no difference whatsoever to an inner product. But you can also move axes parallel to each other and orthogonally. That's good. Up there, that looks orthogonal. In front of me on here, it doesn't. And that's a good illustration of the hazards of trying to get angles right. on this computer here, it has tried to be clever in some way or other and has altered the scaling. So that what was a right angle is now about 120 degrees, 110 degrees, shall I say. It's slightly skewed. One has to watch this all the time. But people who draw simple graphs, functions of x against x, are very happy to move their axes so that the vertical axis is to the left of the diagram, horizontal axis is at the bottom of the page. They don't try and put them through the middle of all their data. And there's no reason why the kind of maps which we look at should have the axes going through the middle of the data. You can move them. And this is because projection anywhere on this line onto that axis and that axis gives it the same value. So it doesn't matter where they are as long as they move parallel in that way. Here is just a little example to illustrate it, very simple example. You don't have to worry about the actual analysis. It's a PCA analysis where there are 4 variables. And this is the same thing, exactly the same diagram, after the axes have been rotated and shifted. So there's no additional or no less information in this diagram from this one. These two contain exactly the same. Here the axes go through the middle of everything in the usual way. Here they've been rotated and tidied up just by these parallel orthogonal shifts, and it looks much more like the kind of thing you find in a physics book. Now, I'm not quite sure where to start with this, except that I can see that something has gone wrong in the process of these sigma to the alphas have got overwritten. That's just one of the hazards of using computers. I'm sure it was all right when I started out. But, of course, we have the singular value decomposition, and we can plot row points, u sigma to the alpha, and column points, v sigma to the beta. And there is, a huge literature. In my opinion, far too much is written about how you should choose alpha and beta. People get very hot under the collar, if I can use an English expression, about choosing alpha and beta. Ideally, alpha and beta should add up to 1 if you want to preserve the inner product. And the easiest way of doing that is to choose alpha as 1, beta as 0, or beta as 1, alpha as 0. That preserves the inner product. And this is quite a useful choice for principal components, because then the u sigma gives you the projections of the cases of the data onto the approximation space. So the distances there are approximations to the distances in the exact analysis. Then the v's give the directions, or the directions of calibrated axes for the variables. You can do it the other way round, and if your background is more in factor analysis than principal components analysis, you may well use the beta equals 1, alpha equals 0 option, in which case you get v sigma, and the inner product of v sigma with itself, of course, approximates the covariance or correlation matrix. And if that is what you want to approximate, that kind of scaling is better. For correspondence analysis, and in France, alpha is 1 and beta is 1 is often used, frequently used. And that is okay. It doesn't preserve the inner product, but it does give you the row and column chi-squared distances. If that's what you want, fine. I like this symmetric one. If you're looking more at the Pearson residuals, or you're operating on what is definitely a two-way table rather than a data matrix, there's no reason why you should give different scalings to the singular values for the rows or the columns, so alpha and half, beta and half. But all these things are available for choice. Again, doesn't matter too much which you use, as long as you tell people what it is you've done. Now, lambda scaling is one which had passed me by until I was talking to Patrick Ronan a year or two ago. So thank you, Patrick, for drawing my attention to this. because in many ways it makes the sigma scaling redundant. Very simple observation. If you have an inner product of that form, you can put in a scale lambda, oh dear, a scale lambda, as long as you put the inverse scaling on the column points. That preserves the inner products. Now, people get very worried if you have two sets of points and one set of points is concentrated near the origin and the other set of points is out in space. Well, you can correct for that by just scaling one set up and the other set down. And the inner product is still preserved and everything that you might want to do is preserved. And you can even be a little cleverer and say if you want the dispersion of the two sets of points to be roughly the same, you might scale them, choose lambda to satisfy this. It says the average value for the row points is the same as the average value of the column points after scaling, which tells you that lambda is determined that way. P and Q are the number of rows and columns. So that's another form of scaling you can use without doing any violence to your data at all. It's just presentation, nothing else. And this just goes on to say that instead of just having a value lambda in there, you could have any non-singular matrix, L and L to the minus 1, and things would still be true, but I don't think this is normally very helpful. It's a rather complicated transformation, although perhaps choosing L diagonal might be justified in some instances, perhaps where L refers to weights. So you can do a lot of scaling of your map without affecting inner products. Just a little bit about nonlinear biplots. And so here is a nonlinear biplot using something called Clarke's distance. We needn't worry about it. It's just what it looks like. So there are a set of points, and then there are these axes which are superimposed in the way which I very, very briefly outlined a while ago. And you predict just by they're calibrated. Here's a point. You drop the normal from there onto there, and you read off the calibration. You drop the normal from here onto here, and read off the calibration, just as you would do with linear axes. In fact, you can do all these things, and again, this is a miracle. On there, it is perfect. In front of me, those circles are ellipses. Again, the software has introduced distortion, which I didn't want. So the thing is, look at this point here. Draw this circle on there, the red circle on there is diameter, and of course the diameter subtends a right angle. So for these kind of axes, that point there gives me the right prediction for this axis, and for that axis, and for that axis, and for that axis. So this circle gives me, reading off the calibrations, where that circle crosses these nonlinear axes gives the predictions for this case, this point. And if these had been linear axes, a conventional sort of biplot, you would again get all the correct predictions just by drawing that one circle. The green circle is just another case. So we call this circular prediction, and with one kind of nonlinear biplot axis, that's how you use it. So this demonstrates a different kind of axis. Now I said I'd say something about category level points, for how we deal with categorical variables. Maybe too much to take in there, so I shall read it slowly. Quantitative variables define a continuum of values represented by continuous, often linear axes. Now, every dummy variable of an indicator matrix, 0, 1, takes those values. So the idea of coordinate axes doesn't work. You take a finite number of these levels. So you take LK levels for a categorical variable which has LK category levels, and that defines LK points, and I term these the category level points. Now, just as the sample with the value xk, a numerical value xk, is closer to the marker for xk on the kth axis, so must the sample with a particular category level be closest to the category level point for that category level. So we're back to closeness rather than projection. Now, there are two common measures. One is chi-squared distance, and the other is what I call the extended matching coefficient. I think Sunya used it this morning briefly. If you have two individuals, a set of categorical variables measured for them, observed for them, you just count the number of matches, just as you would with a simple matching coefficient. And you can work out a distance that way and approximate it by some form of multidimensional scaling. If you choose chi-squared distance, this is on the indicator matrix, you will get the chi-squared distance mapping. And it turns out that the category level points for these two are, for the extended matching coefficient, merely the unit matrix. Just the points 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, no, just those points. For multiple correspondence analysis, you have to bring in the frequencies. The frequencies are given in the diagonal matrix L, so it's 1 over the square root of those frequencies, and they define the category level points. The root P is put in there, that's the number of categorical variables. It doesn't matter, it's put in for tidiness sake in the mathematics. For canonical variate analysis, the category level points are the coordinates of the canonical means. So you can deal with categorical variables through these category level points and treat this as a new kind of coordinate system. Now, the category level points give an exact representation in some high-dimensional space. Biplots, of course, are approximations, so you have to define what you mean by this approximation. Now, I said the category level points in the full space define nearest neighbor regions. If you're using a projection method, you have to slice through all these nearest neighbor regions, and that cuts off convex spaces, convex areas, and you have to know how those convex spaces are represented in the approximation space, and this can be done. And I call those things prediction regions. Here are some cases. This is for multiple correspondence analysis. Prediction regions, you will see the cases. Each panel, there are 5 of them, represents a different categorical variable. Now, this is the one major differences between categorical variables and continuous variables. Continuous variables, you can put them all on one biplot. They're just axes, linear if you're lucky. But if I try and superimpose this is the one. If I try and superimpose that onto that, onto that, onto that, onto that, you can see I just have a mess. So we have to do each categorical variable separately. But having done that, here we are. Here are the cases. These are red, and these are green, whatever that represents in terms of that categorical variable, 2 levels. Here there are 5 different levels. Here there are 3, here there are 3, here there are 3. Now, just to show what would happen if we used the extended matching coefficient, we get the same kind of thing. And in fact, it hasn't made much difference. Except, of course, the annoying fact of software as usual, things have been rotated. So if you focus on this diagram here, it's really exactly the same, or virtually the same as that one there, except it has been rotated through 90 degrees. But the information is the same, and if I switch between them, oops, look at the second one, not so very different. We have the 5 regions in both. They are different shapes. Look at the last one, shall we say, here. 3 regions, 3 regions. but it has been rotated. I think the colors are supposed to match. Red, green, and blue is supposed to match. Red, green, and blue here. Don't know which way I'm going. That and that. So the change of metric hasn't made a lot of difference, at least in this case. And this is something one can study. 5 minutes, thank you. Right, I shall move on very quickly. There's an interesting combinatorial problem. Can we devise a configuration of cases and a set of convex prediction regions that maximizes the number of correct predictions? Now, since I only have 5 minutes, I shall go through these very quickly. This is canonical variance analysis biplots. Here are the variables moved to one side. Here are prediction regions for the different populations. Here is a mixture of continuous variables with categorical variables. The lines representing the continuous variables and the convex regions, categorical variables. One I like here is a nonlinear principal components analysis, which shows the axes shifted out of the region of where all the points are. There are large numbers of points, so these are represented by density mapping, and these being ordered categorical variables, they're shown along as different thicknesses along these different axes. And they can actually be sorted out into sort of bipolar things, one which increases in that direction and one that increases in that direction, and an orthogonal set over there. So it's a nice picture of what's going on. Accuracy. It's very important to know how accurate your diagrams are. People use circle diagrams, which we call adequacy diagrams. These are all right if you're trying to predict covariances or variances. But if you're trying to talk about the accuracy of a particular axis, you can say how good is each axis, and you can attach a number for each axis, and these are attached here. These are called predictivities, and axes which have low predictivity, you might get rid of them altogether because, especially if you have too many axes, you don't want to show those which are no good. Coming more or less to the end, just a little bit about triadditive models. Someone asked me a question about this 6 months ago, and did I know any sort of biplot type technique for representing triadic things? And here is a simple triadic model, and I noticed that you can write it as this determinant. So it is the content, the volume of the points with those coordinates. So that represents the volume, in this case, of a rank 2 triadditive model of this particular form. That has a geometry, and that is that the A, B, and C points all lie in different planes, orthogonal planes. So if you now want to represent the IJK rank 2 fit, it's a matter of taking, say, the J point from here, the K point from here, and the I point from there, and working out the volume of that with the origin. Well, it isn't very, very convenient. It gives you some idea of what's going on and suggests how difficult it might be to get nice geometrical ways of representing content for triadditive models. But it is a rank 2 one shows some possibility. I will just flash this one before you. Rank 3, really horrible, and well, of course we normally look at rank 2 fits for our maps anyway. So just in passing, I do have these remarks and might do some more work on this, which brings me to my final slide. Now, this is 1910, only 20 years before I was born, in a town not far from where my father lived. So I think these people may well be relatives of mine. And the thing which I like about it is that even in 1910, the Gower wagon has been hitched to 2 horses. The white ones represent rows and the black one represents columns. Thank you.